So far in chapter 3, we have discussed simple interest, which was these two formulas, okay? And then we did most of section 3.2 combined with all of section 3.3, and we took a look at the compound interest formula and the future value of an annuity formula, which is this formula, okay? And we discussed the differences, and remember I taught these two equations simultaneously so that you could pick up the difference between the two from the get-go. Both of these you want to use when you're saving money, and the only difference is how often you're making a deposit. With compound interest, it's a one-time deposit. You're saving one lump sum. And with the future value of an annuity, you are making regular deposits into your savings account, okay? There is a portion of section 3.2 that I did not cover initially when I taught these two formulas, and that is this middle formula, which is the continuous compound interest formula. So I am going to shuffle back to section 3.2 and complete this section by briefly discussing the continuous compound interest formula, okay? It is this formula in the middle, okay? This A is equal to P times E raised to the R times T power. You could just kind of call it PERT for if you want to refer to it. It's easy to refer to it as PERT. Basically, if you notice, it is a form of compound interest, okay? So that's why it is in section 3.2 with the regular compound interest formula, okay? So there is a separate packet of notes on D2L for continuous compound interest, so I will be following those notes in a second, okay? But when do you want to use this formula? Well, it is going to be compound interest, so you're still going to be saving money with a one-time deposit or a one lump sum, okay? The big difference here, okay, or how you're going to identify it, that it's continuous compound interest, you're not going to see phrases like compounded monthly or compounded quarterly or compounded, what haven't I said, annually. You're not going to see stuff like that. You're going to see the phrase compounded continuously, okay? So this particular formula is extremely easy to identify when to use it because you're going to see the phrase compounded continuously. And this is the only formula for continuous, compound interest. Okay, so again, we can lump this one into the same kind of category. You are going to be saving money, okay, and it is also for a one-time deposit, okay? But for this one, you're going to identify it by seeing the phrase compounded continuously. All right, so I am going to work through the little separate packet of notes that I made for continuous compound interest. It's very short. I think it's 3 problems, okay, just so we can get some practice with this formula A equals P times E raised to the RT power. Okay, so here we go. This is what the notes look like, okay? All right, again, this is out of section 3.2. There will be a separate MyMathLab assignment for continuous compound interest, so make sure you're aware of that, okay? All right, so let's read about this. The first bullet point there says continuous compound interest is a form of compound interest in which the number of compounding periods per year increases without bound. Okay, so what that means is what's underlined. You can think of continuous compound interest as the interest being added to the account all the time. It is continuously being added to the account, okay? So interest is being added to the account all the time, okay? So again, since it is a form of compound interest, you would use this in a similar situation that you would use the regular compound interest formula, okay, where you are saving money, okay, and it is through a one-time deposit, okay? And again, the way you're going to identify that you will use this formula instead of the other compound interest formula, which is this guy, okay? If you're supposed to use part, you are going to see the phrase compounded continuously. Very easy to spot. All right, so let's talk about this. All right, so it says the formula for continuous compound interest is A equals P times E raised to the RT power, okay? P and A and R and T have the same meanings that they do with the regular compound interest formula. A is going to be the account balance. P is the original deposit, which is one lump sum. R is the annual interest rate, which is always in decimal form. And T is the time in years that the money is invested. Okay. So the new thing is this E. Okay. E is actually a number. You may or may not be familiar with it. Okay. There are some E buttons on your calculator, or there should be. Okay. Let's see here. So what do we have here? We have, okay, I have like the TI-84 Plus Silver Edition. So if you have like some kind of TI calculator, you probably have a similar looking kind of display. If you have questions, you can always ask me about your calculator. There are two E buttons that you need to be looking for, okay? So there is a regular E key, and then there's an E to the X key, okay? So let me show you. First of all, let me tell you what E is if you don't know. E is a number like pi. Remember, we're all used to pi from geometry. Pi is a decimal. It is approximately 3.14. It goes on forever. It does not end. It does not repeat. So E is a similar kind of number, but instead of 3.14, it's approximately 2.71, okay? So these are just the first few digits of E. Okay, so it is a number similar to pi. So if you wanted to find this on your calculator, okay, my E key, just the E, that's going to give you the 2.71 decimal, is on the division key, and notice it's in blue. So I actually have to go and hit the second button and then the division key to call up E. Okay, so if I were looking for E, I would hit second, the division key for E, okay, and that's going to bring up E. And if I hit enter, it's going to give me the decimal approximation for E, okay? So look what I have in big red on your notes, okay? Yes, this is the decimal approximation for E, but do not round this number in your calculations. Do not, okay? It goes back to all this financial stuff that we cannot round until the final answer. So if you started rounding E to 2.71 or even 2.72, it's going to start throwing off your final answer by just a few cents or even more, okay? So you have to use the full decimal expansion, so that's why you need to be using the E or the E to the X button, okay? Notice in your formula, E is going to be raised to a power, so you're probably going to be using mostly, well, you'll probably use both, but you're probably more so going to be using the E to the X button where you can raise E to a power, okay? So that button for me is located on my natural log button, okay? So that right above it, you see E to the X in blue. So if I do second ln, it's going to bring this up in the display where I can raise E to a power. So say if I wanted to raise E to the 5th power, okay? So then I would be multiplying E by itself 5 times, and it's going to do that for me, okay? So those are the two buttons you want to be able to use for continuous compound interest, okay? Again, do not round E, okay? But do have in the back of your brain that E is a decimal like pi. E is approximately equal to 2.71, okay? All right, so here's an example of a problem that is going to use continuous compound interest. So again, just like we always do, we will talk about why we're using the formula we're using, and then we'll identify the variables in the unknown, then plug and chug and solve our problem, okay? All right, so example 1 has 2 parts in it. It says, what amount will an account have after 1.5 years if $8,000 is invested at an annual rate of 9% compounded? In part A, we're going to look if the interest is compounded daily. And then in part B, we will look at how it differs if the interest is instead compounded continuously. Okay? All right, first of all, the entire problem as a whole, you are saving money. Okay, you're taking $8,000, you're investing it in some kind of account. You're saving the money for 1.5 years at this interest rate of 9%. Okay, so since you're saving money and you are investing a lump sum of $8,000, this makes this a compound interest problem as a whole. Okay, so the difference here is how the interest is compounded. Here, the interest in Part A is compounded daily, so you're adding the interest to the account every day. So since you see the phrase compounded daily, you're going to use the regular compound interest formula, okay? Because you will have an M value, okay? So the M would be 365 in this case, since you were assuming a 365-day year, okay? But then in Part B, the interest is going to be compounded continuously, so you're adding, in theory, you're adding the interest to the account all the time. If you're adding the interest to the account all the time, remember, what are you going to use for M? Okay, you can't use like infinity because, you know, you can't really put a number on adding interest to the account all the time. M is how often or how many times a year you're adding the interest to the account. You can't pinpoint an M value for that. So that's why the formula turns into PERT, okay? So as soon as you see that word continuously, you would be using the PERT formula, okay? So that's the difference here, okay? All right, so let's go back to Part A and figure it out, okay? And this is a great problem because you can kind of see how regular compound interest compares to continuous compound interest. You know, you might think, okay, well, since I'm adding the interest to the account all the time, I'm probably going to get a lot more money. Let's see what happens, okay? All right, in Part A, we are looking for, I'll put the variables over here. We're looking for the account balance. How much will the account have after 1.5 years of savings? So we're looking for A. P is the amount of the one lump sum that we are putting in the bank. That's going to be $8,000, okay? R is our interest rate. Remember, the problem is usually going to tell you it's an annual rate. You can ignore that word annual. The interest rate is always an annual rate, okay? You need to convert that to a decimal, so it's going to be 0.09, okay? M, we can actually put a number on it here. So M is going to be 365, since we're compounding the interest every day, or 365 times a year. And then the T value, we're saving the money for a total of 1.5 years, okay? So we're just going to plug all of this in, okay? So A is going to be 8,000 times 1 plus R over M raised to the M times T. So it's going to look like that if I plug everything in, okay? Let me go ahead and partition this off. All right. So then we just have to, you know, put this in our calculator and we will get how much money total. So that's going to include the $8,000 plus any interest that we've earned over the 1.5 years. Okay, so let's plug this in. Make sure you can see this. All right, so plug and chug just like we did in when we were learning sections 3.2 and 3.3 together, just as you see it. So it's going to be 8,000, open parentheses, 1 plus R over M. Close the parentheses, and then this exponent you probably don't want to do in your head, so you need to put it in parentheses. It's going to be 365 times 1.5, close the parentheses. So this is how you would enter this into the calculator, especially if you have an older calculator. Okay, here comes your answer. I'm going to write down the whole decimal expansion, and then we will round at the very end like you're supposed to. So the account balance is going to be $9,156, and then we'll figure out the cents in just a second. Okay, so there we go. And now we need to round it to dollars and cents. Okay, so we've got 14 cents. We need to look at the number after, okay, which is a 1. So we're going to keep it 14. We will not round up. Okay, so after 1.5 years, you have $9,156.14. Okay, so you can see you put in $8,000 initially, so you earned about $1,156.14 worth of interest. So that's not bad. Okay, all right, so let's take a look at what had happened instead if you're compounding the interest all the time. Okay, you might think, okay, I'm getting a lot more money because you're going from compounding the interest from once a day to all the time. Okay. Again, your variables are going to be pretty much the same. You're still looking for the account balance. You still are investing one lump sum of $8,000. Your R value is the same interest rate. You cannot put an M value to this because continuously, all the time, you can't put a number on M. So that's why it's a different formula. There's no M in this formula. You're still investing the money for 1.5 years. Okay, so it's a little bit different because you don't have an M value. Okay, so let's plug into this. It's going to be A equals 8,000 times E. You do not round that to 2.71. You're going to have to use the full E decimal expansion. Raise that to the 0.09 times 1.5 power. Remember, R times T is in the exponent. Okay, so remember that. All right, so let's plug this in and see how it compares to compounding daily. Okay, so we're going to do 8,000, okay, times E. So I'm going to do second natural log to raise E to a power here. Okay, and we're going to get 0.09 times 1.5 is my exponent. This is R times T, close the parentheses. Okay, there's your answer. Okay, so it's a little, let me write down the decimal expansion here. It's a little surprising if you're seeing this for the first time, because you might think since you're compounding continuously, adding interest to the account all the time, that you might get a whole lot more money. Okay, and look how it compares to your answer in part A. Okay, it differs by a few cents. You're barely getting much more money. Okay, so if we go ahead and round this, okay, our final answer for continuous compound interest, you've got 29 cents, and then you've got to look at the number after. It's a 4, so it's going to stay 29 cents. So if you compound continuously, you're getting a whopping 15 cents more. You're going to get $9,156.29 as opposed to $9,156.14 when you compounded the interest daily. Okay, so theoretically, it sounds like you're going to get a whole lot more money, but you don't actually do so, unfortunately. All right, let's take a look at the next example.